Hi, this is Math372 Complex Analysis. This is a supplemental pre-class special lecture invitation only on integrating along curves. And so the idea is to review some of the concepts from multivariable calculus as to how do you actually do these different integrals. So review integrating along curves. So we will assume all curves are nice. They are shapes that will be reasonable to somebody in elementary school. So we have some kind of closed curve. It doesn't intersect itself. What this means is we have a map, gamma, from AB to R2. So you give me a number between A and B, and it maps it somewhere in here. So people often denote it, here's the interval AB, here's the map gamma that takes us there. And typically you'll denote, here's the point gamma t. If it's closed, then you would have gamma A equals gamma B. And then the question is, how should we integrate along the curve? Well, one thing we can do is we can do sort of like a polygonal line segment approximation to the curve. And you replace it with a lot of small polygonal sides. And then for each one of these, we will look at the value of the function at that point. And then we would say, as a definition, the integral along the curve gamma of f. And we might write this as, f of t dt. Well, we've got to be really careful as to what we mean here. Because f of t is not necessarily on this curve. So we can't just write f of t dt. This is very similar to when you're doing the chain rule to remember where do you evaluate when you have f of g of t. It's f prime at g of t. F prime may not be defined at t. This is the point gamma of t. So that's where we should evaluate f. Then the question is, what should we put here? Should we put dt? So we need the length of this polygonal piece. And so if you imagine, something like this. Here is maybe gamma of t. Here's gamma of t plus delta t. And maybe, delta t is b minus a over n. We've chopped it up into n pieces. And we want to approximate this length. So how would we approximate that length? The length of the line segment.
Isn't there like the simple formula from algebra in that? The difference of...
So we'll write this as x of t plus delta t, y of t plus delta t. And then this point over here will be x of t, y of t. So how would you find the length of that?
So x of t plus delta t minus x of t.
Good. So basically, it's the Pythagorean Theorem.
Yeah.
So the length of the segment is going to be approximately the change in x of t squared plus the change in y of t squared square root. And this is what we'll mean by gamma prime of t. And then we have to figure out what do we do here. So if we look at gamma prime of t, that would be, say, x prime of t, y prime of t. So we take the length of gamma prime of t. That's going to be the square root of, I'm going to write it as dx dt squared plus dy dt squared. Well, I want basically dx squared plus dy squared. And so we need to multiply this by basically dt. So we get gamma prime of t dt. And then that will give us the square root of dx squared plus dy squared dt. Yeah, this is the multivariable review. This is what's often not done in multivariable calculus.
I think we did this.
So this is how you integrate along the curve.
Why does the dt show up on the far right side there? Doesn't it get canceled out on the inside of the square root?
Yes. What do you need? We're recording, so whatever you ask for is being recorded.
I was wondering if you happen to know, is there a prize for solving the Goldbach conjecture?
Yes.
Do you know how much it is for?
I will commit myself to something. I will get a prize.
Okay.
Yes. If they solve it, it'll be at least 4 figures.
Okay. Very cool.
Yes.
Thank you.
And for the record, since this is being recorded, $1 could be written as 1.00. That's 3 figures. You know, $10 and a cent is 10.01, 4 figures.
Yeah, wait, the dt shouldn't be on the right because it got canceled right inside.
So let's see. But we have it on both sides. Oh, I see what you're saying.
Under the radical.
Under the radical. Yes. We should still have the dt's here. Yes. When I go like this, you're right. There is no longer a dt here. Correct.
Yeah.
Yes. This is the correct statement, and this then is the length of the segment. So this is why we then say that the integral here, what we want to put in is the length of gamma prime of t dt, and that's why this is the formula for integrating along a curve. So this is integrating a scalar-valued function. So think of f as temperature. Think of f as density. If f is density, this will give you the weight of the rod. If it will give you temperature, it will give you the total heat of the rod. So we can also integrate vector-valued functions. So the formulation is very similar. So now, we still have everything as before, but now what we're going to do is we're going to look at f is a vector. So vector valued function. So what we're going to do here is imagine, we'll often use, I think they use capital letters now. So f of t, you can write it as, p of t, q of t. But then sometimes they put in the gamma explicitly as to where you are. So you might do, there's sadly lots of different ways you can phrase this. But I want a function of 2 parts. And so if I'm doing things in a plane, how do I want to do this? Maybe what I want to do is write it as big F of xy is p of xy, q of xy. You give me a point in the plane, and I have my east-west component of my function, my north-south component. Now I can look at f of gamma of t, because gamma of t is going to give me a point in the plane. And this will just be p of gamma of t, q of gamma of t. And so now, imagine at some point here, this is the tangent. This is the direction of gamma prime of t. And then f of gamma of t is, say, in this direction. And I want to define a line integral. You have some choices. The definition that is very useful in physics and mathematics is to say the line integral is just f dotted with gamma prime of t. It's how much of your function is in the direction of the tangent to the curve. So if you're perpendicular everywhere, there's no contribution. If you're entirely aligned. And so now we can look at what would happen if we did f of gamma of t dotted with gamma prime of t. What would we get in that situation? So we can write this again as f of gamma of t dotted with x prime of t, y prime of t, dt. And so now, let me just try to walk like this and see if I can get this to swing over. There we go. So now this is dx over dt times dt. That's going to be basically my dx. And dy over dt dt, that's going to be my dy. And so this will be essentially the same as before. And now I just do this dot product. and then I just integrate this. And then it all comes down to what are choices of functions and choices of gamma where you can actually do the calculation. In general, it's very tough to do these integrals. The big lie of Calc 2 is that you can integrate. We work really hard, if we care, to find functions that have nice antiderivatives so that you feel calculus is doable. You know, you're young, we don't want to discourage you too much. But as you get older, you realize just how hard it is to find antiderivatives or to find good closed form expressions for antiderivatives. A lot of functions have antiderivatives, but it may not be a nice antiderivative. What is the antiderivative of sine? Or the antiderivative of cosine. Let's do antiderivative of cosine. So the integral of cosine of x dx is sine. Is that a nice antiderivative? How do you calculate sine of a number? It's an infinite series expansion. We've given it a name. And we've tabulated its properties. But it's an infinite series. We're just doing a quick review on integrating along curves. The camera is rolling so that if you missed the review and you want to see the review, you can just watch the first couple of minutes of class. So just because we give it a name doesn't mean we really understand the function or that it's easy to work with. So if you want e to the negative x squared dx, I think this is how it's done. I think it's from well, let's do e to the minus t squared dt from x. This is something like f of x. I'm probably missing square roots and pi's and whatnot because of how the error function is defined. There is a function that is the antiderivative of the integral of the Gaussian from 0 to x. It's given by an infinite series expansion. You have to do some jiggling to make sure that it works. Just because we've given it a name does not mean it's nice. So when you actually want to do these integrals, most of the time the integrals are very hard, unless you're in a situation where Green's theorem can come to the rescue. And then Green's theorem will say that certain integrals are the same as other integrals. This one-dimensional line integral is the same as this two-dimensional area integral. Or this two-dimensional area integral is the same as this volume integral. That's the whole power of Green and Stokes. It's especially nice if it turns out that you're saying it's the same as this integral of 0. We can integrate 0 extremely well. And that's the whole power of Green's theorem, Stokes' theorem. And in fact, in some sense, this is the greatest segue possible to what we're going to do today, because I want to essentially integrate 0. And once we can integrate 0, we will just integrate 0 in clever ways. So it is probably close enough right now that it's not worth stopping the video for a couple of seconds. So we will save the announcement for all time. There's a math colloquium today. Does anybody know what room is it? 106? Okay. I know we're still trying to decide where the colloquiums will be held. Tim will be talking about something related to commutative algebra, or commutative algebra will be talked about Tim. I don't think it matters what order. Okay. So we are going to, it's 9 o'clock. You know, the jokes can't be that good this early, okay? We're going to do Cauchy's theorem. This is going to continue Cauchy's dominance of the subject, okay? There's lots of different things we can do. There's lots of different conditions we can state. So I'm going to assume f is holomorphic. What does holomorphic mean? Complex differentiable. So f is holomorphic on an open omega containing a disk D with boundary C. So if you want, here's omega, here's some disk D, and here's the boundary C. I guess I'll draw it in solid. Then for all z in D, we have the following. F of z is 1 over 2 pi I integral over c of f of zeta over zeta minus z d zeta. And I'll write the n plus first derivative, kind of give away a little bit of the punchline, is the integral of c over c, 1 over 2 pi I, f of zeta over zeta minus z to the n d zeta. There is a small but pitched battle among mathematicians as to which is the better constant, pi or 2 pi. There's a small subset of people who say 4 pi should also be considered in the discussion. These people often do physics, and you see spheres, Stokes' theorem and stuff like that. It really is a worthwhile question. Now, pi is 3.14, so you can celebrate on March 14th. If you did 2 pi, what day would you have to celebrate? June 28th, which is actually two perfect numbers, 6 and 28. Coincidence. But most people aren't in school on June 28th. So there's a natural tendency for students, I think, to gravitate towards pi because it gives you a celebration during the academic year. It's worth thinking, what is the fundamental constant? What is the fundamental thing that we're looking at? Pi is related to the area of the circle. 2 pi is related to the perimeter. And in complex analysis, it's 2 pi that occurs far more often than pi. And in some sense, it's 2 pi that should be the fundamental constant. Or if you really want to get technical, the reciprocal of 2 pi times the square root of -1. But we're not going to go there. There's a limit to. But you really want to think, when you're writing formulas, what's the best way to do things? What's the real fundamental quantity going on? And in complex analysis, it's the perimeter of a circle. OK, so the proof of this. So we will prove initially just statement 1. And then we will see how we can maybe get statement 2 from statement 1. Any thoughts as to what you might use to get 2 from 1? Induction. Not a bad idea when you see the first part is a statement basically when n equals 0, and the next one is n and then n plus 1. Induction seems like a really good way to go. OK, so we want to show that if we integrate f of zeta over zeta minus z over a circle, and z is inside that circle, then we just get f of z. We mentioned in last class that this is an absolutely amazing formula because it tells you if you define the function on the boundary and you want it to be complex differentiable, there's a unique filling in. You don't have that much freedom. Okay? You can think about physics and heat flow and what's going on there. So we want to choose a contour. So what we're going to do is it won't quite be proof by picture, but imagine this is the point Z. And this is our curve C. We'll choose a circle of radius epsilon about Z. Technically, we should choose a different thickness over here. It could be the same epsilon. It could be epsilon prime. It's not going to really matter. We can do the same epsilon. And we travel C counterclockwise, keeping the region on our left. So as we come down like this, we then go around this circle clockwise. Then we come up over here. What is the integral of f of zeta over zeta minus z over this contour? It's going to be 0, because we're integrating a holomorphic function along a contour where the function is holomorphic in the interior. The only place f of zeta over zeta minus z is not holomorphic is at zeta equals z, which is not inside the contour. We now take the limit as this slit goes to 0. And in the limit as that goes to 0, the two almost vertical components, I probably should have drawn it better, cancel. And we're left with just the integral over the outside plus the integral over the inside. So everybody's comfortable with taking the limit? All right, so we take the limit. This is now gone. And we're now left with 0 equals the integral over c plus the integral. Maybe we'll call this c sub epsilon. And I'll write negative c sub epsilon because it has opposite orientation. Well, If I just change the orientation of it, I change it by a minus sign. So this is then the same as 0 is the integral over c minus the integral over c epsilon. We now have the correct orientation. Or the integral over c epsilon equals the integral over c. So that's the big idea, is we reduce the integration of our integrand from the big circle to a small circle centered about the point that blows up. And the idea is we shrink that small circle to be an arbitrarily small radius. And then by understanding the integrand, we reduce it to an integration that's very easy to do. How much is f of zeta changing inside this circle? Not much, right? F is continuous, f is holomorphic. So it's even more than continuous. So in this small set, f of zeta is really not changing that much. So I essentially have the function 1 over zeta minus z, essentially. I'll have to do a little bit of bookkeeping. Well, if I just pretend z equals 0, I'm essentially integrating the reciprocal of my variable. We know how to do that. And now it's just a matter of bookkeeping.
Can you guarantee that, if you know that it's holomorphic in this region out here, can you guarantee it's not blowing up in there?
That doesn't blow up here?
Yeah.
Well, I'm telling you the function f is holomorphic.
Oh,
The function f is holomorphic in the whole disk. So I'm not saying that the function f is holomorphic outside the disk. I'm just saying inside the disk. So inside here, the function f is fine. Now this function is not holomorphic in the disk. So what we're basically doing is we're looking at a very special function. It's related to our function f, but by dividing by zeta minus z, we now have a new function which is going to blow up in a very special way. If you want Taylor expand f of zeta, you'll get f of z plus f prime of z zeta minus z plus dot 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 dot. Now, of course, we don't know we can Taylor expand f, but just morally, if you think about what's going on, if you could Taylor expand, the constant term would have a contribution when you integrate, and then everything else would be nice.
sorry, why don't we know that we can Taylor expand it?
We don't know a differentiable function has a Taylor series expansion. We know the converse. This is why I hate this part of the class.
Yeah, the book even talks that we're going to prove the other.
Right, we're going to prove the other. We don't have that yet. Right now we have analytic implies holomorphic. Later we will get holomorphic implies analytic, and I no longer have to care as to where we are in the semester, and we'll just prove theorems and use this. Morally, that's what you want to say is going on. So when you're doing something like this, you want to get a sense of, is this a reasonable result to be getting? So now let me do things carefully. So what we now have, and I'll put in the 2 pi i's, is we have 1 over 2 pi I, the integral over c of f of zeta, zeta minus z dz, is 1 over 2 pi I, the integral over c epsilon, f of zeta over zeta minus z d zeta. I am deliberately leaving some extra space on the numerator so that I can do one of my 2 favorite things in life. Add 0. And the other one? Right. I almost consider adding 0 and multiplying by 1 the same, so I can also enjoy logarithms. But how do we want to add 0? I agree we want to add 0. If you listen, it's screaming at you how to add 0. Yes, why would we want to add and subtract f of z? Yeah, this first bit over here, f of zeta minus f of z over zeta minus z, as zeta goes to z, that's going to look like the derivative. So now I get 1 over 2 pi I, and you can understand why people often just add the 2 pi I at the end, integral over c epsilon of f of zeta minus f of z over zeta minus z d zeta plus f of z over 2 pi I integral over c epsilon of 1 over zeta minus z d zeta. Because f of z is constant with respect to zeta. Well, we know how to integrate zeta minus z. We just write zeta is z plus epsilon e to the I theta. D zeta is going to be I epsilon e to the I theta d theta. So when we do this integral, so we'd have 1 over 2 pi I integral theta goes from 0 to 2 pi I epsilon e to the I theta d theta over epsilon e to the I theta. The e to the I thetas cancel, the epsilons cancel, the i's cancel. Then you integrate the 2 pi cancels with the 2 pi, and you get 1. So we're integrating our friend 1 over zeta, essentially. So this part over here, this is just f of z. So all we have to do is show that as epsilon goes to 0, this goes to 0. Okay, well, we know that this is going to be less than or equal to 1 over 2 pi times the length of the curve c epsilon times the maximum value of the absolute value of f of zeta minus f of z over zeta minus z. So this is where I'm using a little bit of real analysis. I have a continuous function on a compact set. It attains its max and minimum. Well, since the function is differentiable, this limit exists. So what that means is once epsilon is sufficiently small, this has to be close to a fixed number. So imagine the value of the derivative is f prime of z, probably a good name for it. Then eventually it has to be within epsilon of f prime of z. So this would then be less than or equal to 1 over 2 pi. The length of the curve is just going to be 2 pi epsilon. And then this is going to be the absolute value at most of f prime of z plus epsilon. Well, I'll call it epsilon prime. Yes?
Where did the I in the denominator go?
I'm taking absolute values. I'm just saying this whole thing is less than an absolute value. And so it's got to be close to f prime of z. So you choose any tolerance you want, and if epsilon is sufficiently small, this ratio has to be within that tolerance of the absolute value of f prime of z. Well, this now is multiplied by epsilon, so this goes to 0. And that's the proof. So if I give you a holomorphic function, one of the ways to find out what it equals at a point is to do an integral along a boundary. There are times when that will be useful. A lot of times these results are theoretically useful. They allow us to prove certain things. Okay, any questions on what we've done so far?
So will you say the last justification one more time?
Sure. We know the function's differentiable, right? So as zeta gets very close to z, this ratio has to be getting close to f prime of z. So for instance, at some point, if you want, instead of using epsilon prime, at some point it has to be within 1/10 of the absolute value. And so I can make this part arbitrarily small by letting epsilon go to 0. Now, since this part actually doesn't depend on epsilon, it actually turns out that what does this integral have to equal for every choice of epsilon?
0.
Has to equal 0. I'm just proving it's arbitrarily small, but it actually has to equal 0 at every moment in time. This is very similar to, if you remember, the proof of the fundamental theorem of calculus. So I risk asking that question. But when they do this partition, and you look at the antiderivative, and you subtract the antiderivative of x of n plus 1 minus the antiderivative at xn, and you look at that sum, and you have your special sequence points, the value you get has to be independent of where you're choosing your partitions. But you don't know that at first when you're choosing these special points. So what we're able to show from this is we knew that this integral had to equal that integral. We added 0 in a clever way. This piece just becomes f of z because we're just integrating a nice function. And then we're left with this part. And because the function is differentiable, now we actually don't need the full strength of differentiability here. All we need is that this ratio is bounded. So they sometimes talk about Holder conditions or Lipschitz conditions, stuff like that, if you've seen those terms. We do need f is holomorphic, however, because we need to say the initial integral is 0. So, in for a penny, once we've already assumed that, there's no real need of trying to put in a weaker statement here, because we needed the strongest statement to start the proof to say that the integral equals 0. Okay, any questions on this so far? All right, it looks like it's only about 9:15. So what I think I'm going to do is, rather than doing another example, given that we've just done this, let's do this infinitely many more times and prove the formula for f of n plus 1. Okay? All right, so we're all happy with this proof. Okay. So there's a physics proof of statement 2. So what do I mean by a physics proof? No.
Just differentiate under
Yeah, just differentiate under the integral sign, right? I have this expression. Take d by dz of both sides, right? And you get f prime, and when you take the derivative of this with respect to z, I've got a negative down here, and actually we'll see that there's a mistake in this statement. Yeah, there should be an n factorial up here. There's an n factorial up there. And so if you just keep differentiating, you just say the derivative of the integral is the integral of the derivative, and then you'll get zeta minus z to the negative 1, so you'll get negative 1, zeta minus z to the negative 2, and then you get a negative 1 from the negative z, so the negatives cancel. And then that would give you f prime is the integral with the zeta minus z squared. Then to get f double prime, you would take another derivative, and now you have a zeta minus z to the 2 down below, so you'd have a 2 come out, and then a 3, then a 4, then a 5, and that's where the n factorial will come from. So that's the proof. Okay, how many of you have done in real analysis a justification of differentiating under the integral sign? You actually did do that?
Yeah.
Outstanding. I unfortunately only saw one hand raised. So this means we have to rigorously justify this, or we just have to change the course numbering from MATH to PHYS. Knowing how the registrar's office works, I think it's much easier to justify the interchange than to go through and... Now, did I give you the example where Fubini's theorem fails? The infinite sum, right. So we do have to be careful. You cannot always interchange operations. Later this semester, I will show you how to win $1 million by illegally interchanging operations. Okay? You can probably guess what I'm proving. How would we justify this? How should we take the derivative? What should we do to calculate the derivative of f? Definition. So it's really nice when you don't have much freedom. Always go back to what's the definition, what's the quantity I want to look at. So let's go to proof of 2. So f of z plus h minus f of z over h. This is 1 over 2 pi I closed integral over c of f of zeta, and then 1 over zeta minus z plus h minus 1 over zeta minus z d zeta. And this is just coming from the definition of the derivative. Am I allowed to do this? And I think I need an h. Yes. Why am I allowed to do this? Good. The integral is a linear operator. So I just have two integrals and I'm subtracting. The integral of a difference is the difference of the integrals. Great. That's okay. I'm not doing finitely many integrals. I'm sorry, I'm not doing infinitely many integrals. I'm doing finitely many integrals. Finite is okay. Now, in the interest of time, if you want, we could be looking at maybe the n plus first derivative. I'll just do it like this and then maybe just talk a little bit about how the proof would change if we wanted to just keep marching down the line. This is a little bit easy to say because now we have this expression, we want to simplify this. So the bracketed quantity, 1 over zeta minus z plus h over 1 minus zeta minus z, I cross multiply and I'll get zeta minus z minus zeta minus z plus h over zeta minus z plus h times zeta minus z. The top just becomes h. And the bottom, as h goes to 0, is going to become zeta minus z squared. So as h goes to 0, we get h over zeta minus z squared. And so actually, let me put in the 1 over h here so that will cancel. And that's exactly what we wanted. Notice that since we're on the boundary of the circle, we're nowhere near the point z. We're at zeta of z minus h, zeta of z. Zeta is on the boundary, so here, zeta lives somewhere over here. Here's z. Z plus h is going to be very close to z. It's not going to be on the boundary. We don't have to worry about zeta minus z plus h being 0. So this quantity is going to be a nice quantity. This gives us the derivative of f is equal to what we wanted. Okay? So now let's look at what's going on. Let's assume we know the nth derivative. And so now we have, I think, an n minus 1 factorial here. And now the difference is I will have this to the n minus 1 power, I think. And this to the nth power. So if I was taking, or is it just to the nth power? No, it's to the nth power. Because when we did the first derivative, that would have been n equals 0, because we're looking at the function, and we had it to the first power. So it's...
They should both be n plus 1.
Yeah, I'm trying to think, should they both be n plus 1 right now? So f of n plus 1 is f of n. So, no, I think they should both be n minus 1. They should both be n minus 1. So if we want to calculate the first derivative,
Maybe they should just both be n. We were doing it with like n1,
yeah,
and then we had
right.
those things on the bottom, so it couldn't have been those were raised to 0, or else we would have just had 1.
Right, right. So when this is 1, so if this was n here, this was 1 less over there. All right. This is always the fun part. Is just how do I want to phrase the notation? So let's say we've got it by induction. So we know f of n is going to have an n minus 1 here, and now we want to calculate fn plus 1. So that would be taking the nth derivative, subtracting off the nth derivative. Oh, unless the mistake is over here. That's where the mistake is. That shouldn't be an n.
The book has an n there and an n plus 1 at the bottom.
Exactly. That's the mistake, is the n is here, and the n plus 1 is over here. That's the mistake. And if you think about it, when we did the original one, we had our function, and we have one higher power than its derivative. So when we take the derivative, that's the first derivative, that's an n equals 1, that's a 2 down here. That's an n here, that's an n plus 1 over here. So now if we have the n's here, that should be an n plus 1. Okay, but now we're doing things by induction, so let's assume we know things for the n minus first derivative. Okay. So we did the original statement. We did the case of n equals 1. Now let's do the case of n minus 1. So this should be an n minus 1 factorial. And then over here, this should be an n, and that should be an n. So this should be to the nth power. This should be to the nth power. This should be to the nth power. This should be the nth power. This should be to the nth power. This should be to the nth power. Okay. And now we want to see what do we get as h goes to 0. Well, if you look at this, As h goes to 0, this becomes zeta minus z to the n, zeta minus z to the n. So this is looking like zeta minus z to the 2n. What about the top? Well, as h goes to 0, think of this as a to the n minus b to the n, where a is zeta minus z and b is zeta minus z plus h. How do you factor a to the n minus b to the n? It's a minus b, because if a equals b, it's 0. So it has to have a factor of a minus b. And then it turns out the rest is actually not too bad. It's a to the n minus 1 plus a to the n minus 2b plus b to the n minus 1. And you can see that when you multiply by a, you'll get a to the n, then you'll have an a to the n minus 1b minus an a to the n minus 1b. All the cross terms will cancel. So now all we have to do is put in what a and b are and take the limit as h goes to 0. So as h goes to 0, what do a and b both go to? I'm sorry? Zeta minus z. So now if we look at what happens here, this, as h goes to 0, a minus b is going to go to h. So I'll look at this divided by h. So now a minus b over h, that's actually just equal to 1. And now this goes to zeta minus z to the n minus 1, zeta minus z to the n minus 1, all zeta minus z to the n minus 1. How many of them do we have? We have n, because we start off at a to the n minus 1, and we end up with a to the 0. So we get n zeta minus z to the n minus 1. But the denominator, what's the denominator? It's going to zeta minus z to the 2n. So the whole thing is just going to be n divided by zeta minus z to the 2n minus n is n plus 1. And so the nth derivative will be as claimed. So this is a remarkable formula. What have we just shown? Yeah, it seems like we've just shown if there's one derivative, it's infinitely differentiable, and we have a formula for all these derivatives. It's really looking like there's a candidate for series expansion. The n factorial, if you remember your Taylor series, it's nice to have an n factorial floating around. That could be quite useful. So it seems like we are within epsilon of showing that if you are holomorphic, then you are analytic. Right? And it will be amazing how many consequences we will start getting from this. In Friday's class, we will prove the fundamental theorem of algebra. But we will not give an algebra proof of it. We will give a complex analysis proof of it. There are not that many fundamental theorems that you know. You know, fundamental theorem of algebra, what else have you seen? Calculus. There's at least one other one that you've seen, and one other pretentious one that doesn't really deserve the title, but sometimes gets it. Fundamental theorem of arithmetic deserves it. That's 3.
Invertible matrices that you're talking about?
There's the fundamental theorem of linear algebra they sometimes talk about, and I really don't think that quite merits the fundamental.
Yeah.
It's a nice theorem, but if you have to ask what is it, conversation is over. Okay? It's got to be so clear that, oh yeah, that. Okay. So what I want to do now is I want to do an example. So let's say f of x is sine squared x over x squared. And I want to integrate from minus infinity to infinity of sine squared x over x squared dx. What's the first thing you should ask? Does it exist? So it blows up at 0, so I need to check that, and I need to check how it decays. Is it decaying fast enough? Yeah, it's decaying like 1 over x squared, so that's fine. Near 0, what's sine of x over x? 1. Okay? So on a personal note, I got into trouble many years ago when I was an undergraduate. You may find this hard to believe, but I was a little bit of a smartass. And I was taking complex analysis, and we were given this problem. And we were supposed to do this using complex analysis. And so we want to write this as a contour integral, right? So you can write sine as e to the ix minus e to the minus ix over 2I. And this is the same as sine of x. Now, if I square it, I'm going to end up having 3 terms. I'll have to worry about how do I want to handle everything. Okay? What are our 2 favorite techniques of integrating real-valued functions? Integration by parts. And there's one other. U substitution. Okay? So we've got u dv. Do you want to have, well, what do you want for u? What do you want for dv? Any thoughts? Well, I'm looking at this entirely real. Remember, I'm trying to be a smartass and get out of doing complex analysis. All right, so let's try u as sine squared. And let's try dv as 1 over x squared dx. So then v is negative 1 over x. What is du? It's sine 2x. It's 2 sine x cosine x. But 2 sine x cosine x is the same as sine of 2x. Okay? This is the same as the integral from minus infinity to infinity of sine of 2x dx over x. Now, there's no boundary terms, because when I look at uv at the boundary, that's 0. Now I have a minus v du, and the minus sign cancels the minus sign. Dx over x is the same as d2x over 2x. This is the same as the integral from minus infinity to infinity of sine of x over x. Now the question is, how do you know that it's pi over 2? Now, to show that this integral converges is a little bit harder. But what's nice is you have alternation because sine is oscillatory. With some work, you can talk about this. So interestingly, a day or so before my journal exam to get my master's at Princeton, I was reviewing a bunch of notes, and I reviewed this problem from complex analysis. And they actually asked me this integral on my journal exam. And I asked, well, because this was the complex portion of my journal exam, do I need to use complex analysis to solve this? Go, no, do whatever you want, Steve. And so I did this, and then they gave me generalizations of the Fourier transform, which was, because it was fun. It was a lot of fun to see and to be pushed like that. But before you do any math, you should really think what math is worth doing. Can I simplify the expression first? So I consider Henry David Thoreau the patron saint of mathematics. How many of you have read Walden? The big advice, simplify, simplify. Before you spend a lot of time doing a calculation, can you see if there's an easier one to do? Which would you rather do contour integration on? Sine squared over x squared or sine over x? I'd rather do sine of x over x. You've got to be a little bit careful maybe about whether or not things converge. But if we're doing things symmetrically, we're going to be okay. And what you can notice is, because sine of x over x is decreasing in absolute value when you look at the contributions in segments of length pi, you'll have an alternating sum of terms going to 0, so the integral will exist no matter how you go to infinity. So if you try to do the Cauchy integral, the mean of the Cauchy, x over 1 plus x squared dx, if you go from minus a to 2a, this converges to the natural log of 2, I think, as a goes to infinity. It matters how you go to infinity for something like that. Because each of these segments is of decreasing contribution, you're actually fine in terms of how you go to infinity. So let's do this integral. So all I will do now is I'll erase the 2's. And let's do this in full excruciating detail. So sine of x is e to the ix minus e to the minus ix over 2I. The other way we could look at this is we could look at sine as the imaginary part of e to the ix. These are the two different ways to proceed. If we do that, if we look at then cosine plus I sine, if we look at the e to the ix, well, cosine is even, x is odd, and if we do this over a symmetric region, we're fine. So what we want to do is it's enough to look at the limit as r goes to infinity. And if we take that, we could actually replace sine of x with e to the ix and then just take the imaginary part. We don't have to worry about the contribution from cosine because that's going to just give us 0. So it all comes down to which is the easiest way to go. If we do something like this, we have to split the contour and do each part separately, because this part is going to be fine in the upper half plane, but it's going to blow up in the lower half plane. This one's going to be the opposite. If I do it this way, I only have one thing to worry about. Any preferences as to which way people want to go? The second one. Okay, so we'll do that. And so what we want now is we want the limit as r goes to infinity. Now we want the imaginary part. So we're going to have the integral from minus r, it's a terrible r, minus r to r of e to the ix over x dx, and we'll have to put in a 1 over I. All right, so now we need to choose our contour. We have to be a little bit careful. Where is this function problematic? At x equals 0. So our function is going to be f of z is e to the iz over z. We can't have a contour that goes through 0 because the function blows up there. So we have two options. So really, there's 4 ways this lecture could be going right now. And I did prepare all 4 possibilities, and I have contingencies for whatever choices you guys make. All right? So we come along, do something, come along, and go along. All right? We have 2 choices. What are the 2 choices? Go up or go down. Which do you want to do? Go up or go down? Go up. Yeah, because if you go down, then you have a place that blows up. So it's better to go up like this. And now, by Cauchy's theorem, what's the integral over this region? Cauchy's theorem is wonderful. Okay? When in doubt, if you have to guess the value of an integral, what should you guess? Best chance is 0. Right? So we know, let's give these names. We'll call IR I minus R, we'll call C epsilon, and we'll call circle of radius R. So we know the 0 is equal to the integral of over I minus R plus the integral over C epsilon plus the integral over, oh sorry, this is I minus R over IR plus the integral over CR. Should I have a 1 over 2 pi I in front of all of them?
Technically, but it's unnecessary.
It's unnecessary because it equals 0. So you can decide whether or not you want that. But you just have to make sure that you're consistent. When we integrate this, it's actually nice to have the 1 over 2 pi I because that's going to cancel things out nicely, but it doesn't really matter. What can you tell me about the integral over one of these is going to be really easy? Which one is going to be easy to show as small? The CR. Okay, so claim small on CR. Let's think about what's going on there. So you'll have e to the iz over z. This is e to the ix, e to the minus y over x squared. Well, let's do absolute value. And then when we take the absolute value, that's going to just be 1. and we'll have R. What's the perimeter of CR? Pi r. Crap. The r's cancel, but e to the minus y is not small if y is small. So we have to do a little bit of work to show that it's small on CR. As long as y is ever so slightly large, we're okay. So what we do is we split this. Here, let's say this is y equals the square root of r. Okay? Once y equals the square root of r, then we have exponential decay and we're fine. Correct? How long is the curve if we go all the way up to y equals square root of r? What's the arc length? On the order of square root of r. Put in like a 5 square root of r to be safe. So it's a nice exercise prove that if you go up to y equals the square root of r, this is on the order of at most 5 or 10 square roots of r. That's now enough so that the dividing by r is okay. So we have to just be a little bit careful, and this is one of the problems about having x and not x squared. So the other one is a little bit nicer in that regard because you have a little bit better decay. We have to be careful. We have to say, well, if y is really small, then we don't have the exponential decay, but y can't be small for long. So the whole thing has length r. Y can only be small for a very short period of time. And for that period of time, the r down below dominates. Once r gets large, like square root of r, and square root of r is negligible relative to r. I could have even gone up to y equals r to the 1 minus epsilon, and I'd be fine. So is everybody comfortable that the integral over CR tends to 0? This is a really important technique that you can just trim it. Is that okay? You look a little bit... So do you...
How would you, if you were doing something similar, how would you know to choose that?
Experience is I want the exponential decay. Once r has any r dependence, I win. I could even choose, instead of square root of r, I could even choose log of r. And if I put y equals log of r, e to the minus log of r is 1 over r. I need only y to have some small r dependence. Any r dependence in y is enough. And if I take just log of r, then you can see, wow, that's a really short little bit over here. And because I'm dividing by r in the denominator, it's not going to matter. So the contribution over CR tends to 0. The contribution over I minus r and IR is going to the integral we want. So this is what we want. And now we're left with just the integral over C epsilon. And so now we have the integral, let's put a 1 over 2 pi I in, of C epsilon. And now we have a e to the iz over z dz. Let's think about what's going on here. Remember, we're integrating in the wrong direction. Right? So there's a lot of different ways to do this. I don't want to explicitly write z equals epsilon e to the I theta, because I would have an exponential of an exponential. Use e to the iz is 1 plus nice. We know the exponential function. This is going to be something in z squared, something in z cubed. This whole thing is going to be of order z. Right? This is order z. How big is z? It's of size epsilon. What's the perimeter of this? Of size epsilon. I have a z down below that's of size epsilon. So what I would get is everything other than the 1 gives me something of size epsilon, divide by something of size epsilon that's of size 1, but then I integrate it over something of length epsilon. That will give me a contribution of size epsilon. So it's really good to just go through and write all the details rigorously. But the contribution from the nice part over there is going to just be of size epsilon. So we're left with, this is basically equal to error of size epsilon plus 1 over 2 pi I, and then we have the integral of 1 over z dz over c epsilon. And now that's an integral we can do. So now we'll write z is epsilon e to the I theta. Theta, where does theta go from? It goes from pi to 0. And so we'll get 1 over 2 pi I, integral theta goes from pi to 0. And then dz over z, it's going to be I epsilon e to the I theta d theta. We've done numerous times over epsilon e to the I theta. Epsilons cancel. E to the I thetas cancel. The I cancels. The theta integral is now going to give us a negative pi. So this gives us, I believe, negative pi halves. So what we get is we get 1 over 2 pi I, the integral over negative r to minus epsilon, plus the integral from epsilon to r of sine of x over x is equal to, we bring this over to the other side, and we get a pi halves. No, we got the minus I, the 1 over I that I got to remember to put in correctly.
Do the pi's cancel?
Oh, let's see. Oh, the pi's probably cancel. Yes. Thank you. Okay. And so now we want to keep the 1 over I here, for our answer. And so what so if we keep the 1 over I, when we amalgamate that inward, that's going to give us the sine of x over x. Without the I, we have e to the ix over x. And so if I absorb the I now get the sine x over x. I now move the 2 pi over to the other side, and now we get that our integral is just equal to pi. So the real thing is, if I have the I over here, I have to leave this as e to the ix over x. But since the cosine part integrates to 0, if I just absorb the I, it's then the same as integrating over sine. And now I can just drop the I and get sine of x. And we'll be left with, this integral is just equal to pi. Try to do this integral using just real variable techniques. So there's a great quote that oftentimes the shortest way to a proof or a result for real numbers is through the complex plane. It's amazing the power you get working with complex analysis. We can handle integrals like this without too much trouble. The first time you look at this, it looks like it's a lot of trouble. As you get older, you never go through and say, oh yeah, let's carefully chop it up like this. Oh yeah, that's negligible. I remember the first time I was teaching complex analysis, I was showing one of these techniques, and I forgot that it was the first time the students had seen it. So something that takes 5 minutes in math research papers, because everybody's seen it 100 times, is a 30-minute digression to show that, yes, technically what you do is you chop it up a little bit like this, and then you go through. Yes?
I think I missed the bit where we dealt with that little bit that we chopped.
Well, so the length of that arc is going to be on the order of the height of y. And so the value of the function, it's e to the iz over z. Every point here, the absolute value of z is r. We have an r in the denominator. The numerator is going to be bounded by 1. And so now we have something of size 1 over r, and we integrate over the length of those arcs. The length of this arc is small. If y is of size log of r, there's no way that this arc length is even square root of r. It's going to be maybe twice log r at most. So it's a good exercise, figure out what would be the angle that would correspond to y equals log of r. So if you want, to do the calculation really rigorously, this is what you have. So here's r, here's theta of r, and this height here is the log of r. So figure out what angle corresponds to this triangle. Here's the hypotenuse is r. And then you can figure out what that arc length is. Because this arc length is just r theta of r. And so all you need to do is figure out what is theta of r in terms of log of r and r. Well, the sine of theta of r is going to be the log of r over r. So if theta of r is really small, sine of theta is approximately theta. So this tells you theta of r is approximately log of r over r. So this length here is approximately log of r. So it's a good exercise. Just make that argument rigorous. Okay? All right. It takes a long time to do these calculations at first. And if you are having trouble, please let me know. Happy to discuss. If you want me to come in early and just do more examples, I'm happy to do more examples and then just record them as well.